because we are tackling one of the most fascinating, yet profoundly misunderstood, technological leaps of our entire generation. I'm talking about quantum computing. Now, for a long time, quantum has kind of felt like pure science fiction, right? Or honestly, maybe just magic. I mean, these machines literally operate at temperatures colder than deep space. But today, we are cutting straight through the hype and heavy jargon to look at the actual reality of quantum technology. Whether you're a student eager to understand the future of tech, or a business leader trying to figure out if your company is already falling behind, this explainer is totally built for you. We're going to go on a clear, structured journey, moving from the basic building blocks all the way to the critical business strategies you need to be thinking about right now. But before we get into the weeds, let me ask you a question that should, frankly, make every single business leader and security professional sit up a bit straighter. Is your data already in the hands of a quantum hacker? I know, it sounds like a sci-fi movie plot, but the reality is threat actors are intercepting and hoarding heavily encrypted data today. Why? Because they're just patiently waiting for tomorrow's quantum computers to unlock it. The stakes literally could not be higher. And before we finish this explainer, you're going to understand exactly why this is a ticking clock for global cybersecurity. Here is our roadmap for today. Number 1, the magic of quantum basics. 2, from noise to quantum utility. 3, real-world applications today. 4, AWS versus Azure quantum cloud. And 5, the post-quantum security threat. All right, let's kick things right off with Section 1, the magic of quantum basics. Think about the device you're watching this on right now. Our everyday computers, from your smartwatch to massive supercomputers, they all run on classical bits. And these bits are incredibly rigid. They act exactly like light switches. They are strictly limited to being either a 0 or a 1, off or on. But quantum computers use something completely different called qubits. And qubits? Well, they don't play by traditional rules at all. They are fluid. A qubit can be a 0, it can be a 1, or incredibly, it can be a combination of both simultaneously. That brings us to our first really key quantum concept, superposition. This is the ability of a qubit to exist in multiple states at the exact same time. Let's visualize this. If a classical bit is a coin sitting flat on a table showing clearly heads or tails, a qubit in superposition is like a spinning coin. While it's actively spinning, it's just a blur, right? It is both heads and tails simultaneously, at least until it finally lands and stops. This wild ability to represent multiple possibilities at once is what gives quantum systems their incredible initial power. And if that wasn't mind-bending enough, we also have a concept so strange that Albert Einstein himself called it spooky action at a distance. It's known as entanglement. This is a quantum phenomenon where the state of one qubit becomes instantly linked to another, no matter how physically far apart they are. Imagine two of those spinning coins we just talked about. If they are entangled, the exact moment you force one to stop and it lands on heads, the other coin instantly, magically lands on heads too. By combining superposition and entanglement, quantum computers can explore vast oceans of solutions in parallel, operating at speeds that make traditional computers look like they're just standing still. Moving right along to Section 2, from noise to quantum utility. Okay, let's ground this in reality for a second. Today, we are in what scientists call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Simply put, it means today's qubits are incredibly fragile. I'm talking so fragile that the slightest change in temperature or even a stray cosmic ray can cause them to lose their quantum state. This problem is known as decoherence, and that is the noise we're talking about. But the ultimate goal, the holy grail projected for the late 2020s by leaders like IBM, is fault tolerance. This means future systems will be error-corrected, highly scalable, and super reliable. We aren't fully there yet, but we are making massive, massive strides. Which leads us directly to a buzzword you absolutely need to know: quantum utility. Now, even though we haven't reached total quantum advantage, that's the point where quantum entirely replaces classical computers for all problems, we have officially entered the era of utility. Quantum utility is when a quantum computer can reliably perform computations at a scale entirely beyond brute force classical simulation. Essentially, it means these systems are now useful, practical tools for exploring complex scientific problems that our absolute best traditional supercomputers just cannot handle perfectly. Let's look at how this actually builds into a practical workflow for researchers today. Step 1, they take a problem that's simply way too large for a regular computer to solve exactly. Step 2, they run this complex model on a 100-plus qubit quantum device. And step 3, this is the magic part. Because classical computers previously had to just guess or approximate the answers to these massive problems without any strong guarantees, Researchers can now use the highly reliable quantum results to actually check and verify those classical approximations. Quantum is essentially stepping up to serve as the ultimate answer key for our hardest problems. Let's get practical in Section 3, Real-World Applications Today. The parallel processing capability of quantum is set to completely revolutionize some very specific sectors. Let's look at medicine. It allows for the design of life-saving drugs by simulating the exact quantum behavior of molecules, something classical computers completely fail at. In logistics, organizations like Toyota are already using quantum-inspired models to optimize massive global supply chains, routing things with maximum efficiency. And over in finance, major institutions are exploring how to analyze incredibly complex market risks and build advanced investment portfolios. This isn't just theory anymore, folks. It is literally the next frontier of competitive advantage. Next up, Section 4, AWS versus Azure Quantum Cloud. So the good news here, you absolutely do not need to build your own super-cooled, multi-million-dollar quantum laboratory to get started. The big cloud giants are bringing it to you, but the two major leaders approach this very differently. Microsoft Azure Quantum takes what we'll call a deep approach. They've built their own programming language, Q#, and they focus heavily on end-to-end enterprise integration and hybrid workflows. They basically want to own the whole stack. On the flip side, Amazon Bracket takes a light approach. They act more like an orchestrator, offering a super flexible, Python-friendly quantum-as-a-service model. AWS focuses on vendor neutrality, giving you access to a wide variety of third-party hardware. Your choice really just depends on whether you want that deep, enterprise integration or open, developer-focused flexibility. And finally, we arrive at Section 5, the post-quantum security threat. Okay. Remember that hacker we mentioned at the very start of the explainer? Well, their strategy is called Harvest Now, Decrypt Later. Adversaries, and yes, this absolutely includes nation-states, are actively intercepting and hoarding heavily encrypted corporate and government data right now. Sure, they can't read it today, but they are patiently storing it in massive data centers, just waiting for the day when a mature quantum computer can easily smash through our current encryption and unlock all those secrets. Get this. 31%. According to the Global Risk Institute, there is a 31% probability that standard RSA 2048 encryption, the security that currently protects almost everything we do online, will be completely breached within 2 decades. That renders our current digital protections basically obsolete. To understand your actual risk today, researchers use a really pragmatic framework called the Mosca inequality. It works like this. Take the shelf life of your sensitive data, basically how long it actually needs to stay a secret. Add that to the time it will take your massive organization to successfully migrate all its IT systems to new security standards. If that combined number is greater than the time we have remaining until quantum computers can crack encryption, well, your data is already effectively at risk. It's a simple, pretty terrifying equation that absolutely demands immediate action. Let's map this out on a timeline so you can really visualize the urgency here. In August 2024, NIST officially released the very first finalized post-quantum cryptography standards. They are basically telling the world, hey, the rules have changed, start your migration now. Looking ahead to 2030, IBM projects the realization of practical, scalable quantum computing capabilities. And by 2046, we hit that 20-year window where there's a high probability of total encryption compromise. The clock isn't just ticking, the alarm is ringing. So, I'm going to leave you with this final thought. Are you preparing for the quantum future, or are you just waiting for it to break your security? The era of quantum utility is officially here. The hardware is scaling up, cloud platforms are making it super accessible, and the security threats are very, very real. The organizations that are going to thrive tomorrow will be the ones that understand and prepare for this technology today.